I hope you don't think that polysaccharides are the only macromolecule that can store energy, and I really hope you don't think that polysaccharides are the only macromolecule that have functional things in the cell, because if you think that, you're wrong. You know, there's a surgery that's so common these days called liposuction. Liposuction. Well, the suction part of this is pretty easy, liposuction. I've never had one of these myself, as you probably can tell. But what you're sucking out of a person's body when you do a liposuction are not their lips, but their lipids. Lipids. And that's what I want to talk to you about today. The lipids, and some of the lipids that are important in this whole idea of energy storage. Lipids belong to, polysaccharides and carbohydrates are named by their structural formula. Remember that carbohydrate meant carbon, water. And you could tell a carbohydrate by looking at its formula. You know, for example, that C6H12O6 is indeed a carbohydrate because you see a 2-to-1 ratio of hydrogen to oxygen and carbon with that. C, H, and O in this ratio always means carbohydrate. But lipids are not going to be that way. Lipids are determined by their solubility. That's our definition of lipids. Lipids are insoluble molecules in water. They are molecules that are insoluble in water and have several roles in the cell. So remember that. Some of the things I'm going to show you as we discuss lipids, you're going to look at them and say, well, how am I supposed to know that that's a lipid? And the answer is, well, they're nonpolar molecules that are insoluble in water, and this is going to bring us to a whole group of different entities. Let's talk about the lipids close to my heart, fats and oils. Fats and oils. And you know, when you get to my age, you start worrying about these things being close to your heart. Although fats and oils are not horrible things. Fats and oils. Well, I want you to think of some examples. All right. Well, we know the fats and oils. We know about fats, but what about oils? Fats are things that we think of in animals. What's the difference between a fat and an oil? Well, examples. Well, we know corn oil, right? How about, well, it's animal fat. Corn oil. You know, do oils, now we know that animals, they're animal fat, corn oil. Is that the difference between fat and oil? The fact that animals make fat and plants make oil? Well, no. Even though there is, you think of corn oil and sunflower seed oil and things like that, there are animal oils too. Think of mink oil. You know how many minks they have to squeeze to get mink oil? And I've often wondered about baby oil. Well, we better move on. Okay, so anyway, let's go on and talk about what makes something a fat or an oil. Fats by definition, and this is really the only difference, fats by definition are solid at room temperature. Room temperature, depending on what room you're in, roughly 20, 24 degrees Celsius. Okay, so fats are solid at room temperature. Oils are liquid at room temperature. That's it. And in fact, you guys probably know that if you take an oil, pop it in your refrigerator, it solidifies. So then, therefore, there must be something chemically significant to make something a fat or an oil. And now we can get into some great biochemistry. Let's talk about something called triglycerides. Now we're talking fats and oils, and you can recognize a fat and an oil by the fact that it's going to be a triglyceride. Okay. Dehydration synthesis comes into play still again. I know you know about dehydration synthesis. Quick reminder, dehydration synthesis is making something new, synthesizing it by dehydrating it, removing water. So you're freeing up bonding sites and you're popping out a water molecule so you can bond carbons and carbons together so you can make carbon chains. I want to show you how you make a triglyceride. Now, a triglyceride, the basic building block of a triglyceride is a molecule called glycerol. Glycerol is a very, very simple alcohol. It looks something like this. It's got 3 carbons, like so. And in addition to the 3 carbons, it has, well, what do you know? I have one professionally produced right here. And there is a triglyceride. Now, well, not a triglyceride, a glycerol molecule right here in blue. CCC, as I was showing you, 3 OHs, and the rest of the bonds saturated, if you will, with hydrogen. Now, notice we have that green colored in right there. All right, why? Well, what we're going to do is we're going to add a molecule to this, we have to bond at the OH site. So we have 3 OH sites that we're going to bond at. 3 OH sites, triglycerides, hey, it makes sense to me. All right, so what we're going to do here with this triglyceride is we're going to bring 3 molecules in there. Well, what are those molecules going to be? Well, not only do we have glycerol as part of our backbone of a triglyceride, but we're going to put in there molecules called fatty acids. Now, I want you to think of your functional side group stories. Remember the functional side group, the carboxyl group? I hope you're going to be looking for a carboxyl group. Remember, there's going to be something connected to it, and then there's going to be a double bonded oxygen in there and an OH. Okay, that's my carboxyl group. Well, gee whiz, take a look at a typical fatty acid. A typical fatty acid is going to have a chain of carbons. And in that chain of carbons, we're going to find just about everywhere hydrogens. Now, one thing I want you to understand about this that's very important is the nonpolar nature of this fatty acid. Remember what polarity is all about. When you have O's and H's and bonds and a carbon that is not equally surrounded, well, then we are going to find polarity. Well, what you have here is carbons saturated, ooh, there's a term for you, saturated with hydrogens. So, as we go through the saturation of hydrogens, you can see that this thing is going to be completely nonpolar, which is one of the reasons why fats, oils don't mix with water. Anyway, that's not what I'm here to tell you about. I'm here to tell you about the dehydration synthesis. So, very simple. OH and H are going to bond together. That's going to come off as a water molecule. The water molecule itself will be released, dehydration, and then you have this oxygen here ready to bond. And we're going to form something called an ester linkage. And we'll see that when we form a triglyceride, we can make ourselves an ester linkage. And here is that ester linkage right here, all right, boxed in the red. The carbon that was once part of the carboxyl group is now going to be linked by that oxygen to the glycerol backbone. And we're going to do that 3 times. That is a triglyceride. Now, fats, oils, triglycerides. One of the things I want you to understand about triglycerides is what they're used for. These are big-time energy storage molecules. Big-time energy storage molecules. Now, why do we store these as energy? Well, it's kind of interesting. If you take a look at this, you'll notice that there are an awful lot, as I said, of carbons. Now, you know or may not know about a process called respiration. Respiration burns glucose and burns fat by breaking bonds. The more bonds you have, the more energy you have stored. The more energy you have stored, the better the thing is for storing energy. Fats are not as bad as they seem.